Okay, so I will discuss about basically the same topic, but on the very experimental side. And we are using here an STM, and we don't use light to put light on our system. We just look at the light that is emitted by the tuning current that goes to the molecule, and I will show you how we can make some kind of fluorescence microscopy of single molecule with this technique. And just to say a few words about single molecule fluorescence, I mean, people have struggled at the beginning just to catch single molecule with lights, and one of the doesn't work well. Okay, one of the things you can guess. So this is tons of chromophore in a liquid, and what you want is to address just a single of them. And here I quote a sentence from Michel Ourid, that is really a specialist in this field, and he wrote something like this in his website: "Even with the best possible optics, we can never even come close to resolution corresponding to the dimension of a single molecule, so sub-nanometer scale." And now Javier spoiled everything, but anyway, I mean, at that time, people didn't know how to reach single molecule. And the strategy was, okay, first thing, we can dilute the molecule in our solution so that you can address maybe more easily one of them. And then you can take a laser and just focus your laser on one of these molecules. And that's what they call spectral selection. For that, they put molecule also in frozen matrices so that the molecule don't move in every direction, and then you can address a single molecule. And well, when this is not enough, they have another trick, that is spectral selection. So what you have here is how your system would respond to laser. So it's frozen matrices with tons of these chromophores. What you see is the main resonance of all these molecules, and you see also tons of tiny peaks. And each of these tiny peaks that you enlarge here and here correspond to one single molecule. And why is it different for each of them? Because each of these molecules has a tiny different environment, so its optical gap is slightly different in energy. And what they are doing here, they are just detuning the laser progressively so as to match just one of those. And by this way, you can measure the absorption of a single molecule or the emission of a single molecule, and that has been shown in the late 80s by Mörner and Ourid sequentially. And for that, this guy Mörner received the Nobel Prize. This also has a lot of consequences in biology and chemistry with the development of what people call super resolved fluorescence microscopy. I mean, you can look at the fluorescence of a molecule as a function of its distance from, let's say, any bacteria or any environmental change in the range of some nanometer. You would be able to detect it through the fluorescence of the single molecule. So now, by using purely optical method, what people have shown is that one can get a resolution. So this is, I think, one of the best results in the field, up to 5 to 10 nanometers. So that would be the absorption of the small dots here. That would be a single molecule. Okay, so that's very nice. But now, I mean, the question I wanted to quote is can we somehow question the statement of Michel here? I mean, is it possible eventually to reach some sub-nanometer scale resolution? And if we can do that, if we can access a lower scale resolution in optics, what would we learn? I mean, can we learn something about the environment of a molecule? Can we even go further? Can we imagine to look within a molecule and see what would it mean to look at the fluorescence of a subpart of a single molecule? So to do that, I mean, as I said, we want to use a scanning tuning microscope. So you have here a sketch of the junction of an STM tip and a gold electrode. So this is gold-gold junction. And the first thing to realize is that we are in what we call a photon counting regime. So we have some photons, but the amount of light is very low. So to collect this light, no, definitely doesn't work. So to collect this light, what we use is here in our setup. So this is a low temperature system. We put here lenses whose focal point is at the STM tip junction, which allows us to collect as much as the light that is emitted there. Actually, I say as much is probably we collect 10%, and at the end we really detect 2 or 3%. But this is enough to what we have to do. So this light is collected there. It's redirected outside of the vacuum chamber, and well, we use photodetector or spectrometer with CCD to get the spectrum of the emitted light. And after a couple of years, people have determined that this is the process that is beyond this emission for a gold-gold junction. So you have here an energy scale with your tip and your sample. And well, if you apply a bias in between these two electrodes, then you have an electron that will go from this very high energy. Actually, most of them will just tunnel ballistically through your junction. But you have a small fraction of this electron that would lose energy within the barrier that we call inelastic electron. And if you apply a voltage that is high enough, let's say 2 volts, then you can have an electron that will lose up to 2 eV in their junction. And this energy will be transmitted to photon. Actually, there is one step more that Javier already mentioned, is that you have plasmon that amplifies this phenomenon. So light emission in an STM is a combination of inelastic electron and an amplification by localized plasmons. So that plays a role, of course, on the energy, but also on the spatial distribution. I mean, you have the electron that have a given spatial extension, which is really low, but also the plasmon that are localized. That's what Javier has demonstrated, and you will see that this is really something that we have to account for when we try to understand resolution in this experiment, is that we have the resolution of the electron and of the plasmons. Good. So from this sketch, you can already intuit that, plasmon electron. That if you put a molecule in the barrier, you would have some discrete energy level. And if you're lucky enough, maybe there is a way that you can put an electron in one of the unoccupied state of the molecule, and that this electron would decay within the molecule to produce a photon. And in this case, it would be close to what we would call single molecule fluorescence. So that was the early idea. Actually, what people realized very fast is that as long as the molecule is in contact with the electrode, actually this channel of decay from this state to this state is quenched, because your electron would rather go directly to the electrode. So I don't speak about optical quenching that was mentioned before, I really speak about electrical quenching. I mean, maybe you can drive your molecule to an excited state, but rather than decaying by producing a photon, this energy will decay directly to the metal, or at least the electron would decay to the metal. So some kind of charge transfer quenching. Good. So the trick that people use is to work with this double tuning junction. So you put a barrier in between your molecule and your electrode. On one side, it would be vacuum, of course. On the other one, you can use different things, you will see. But then in this case, you can somehow change the quenching path. I mean, you can somehow make sure that the lifetime of the excited state would be longer by preventing this excitation to go directly by charge transfer to the metal. Okay? And recover some fluorescence. At least the naive scheme is there. Good. So that has been done for the first time by Wilson Ho in 2003, where you can see here you have this metal electrode. You have a kind of oxide layer that is one or two monolayer in thickness. And you have a porphyrin molecule, I think, on top. And they run electron to that, and they look at the emitted light, and this is the spectra they obtain. So you have here intensity as a function of wavelengths. You can see that you have one main peak here, that is the fluorescence of the molecule. Or actually, they didn't exactly know which transition it was, but you can even see some vibration on top of it that were related to different vibrational state of the molecule. So that was really the first results, and I think it's really the pioneering work in this field. And from there on, so 2003, there has been very little success in this field. I mean, two other papers from the same group, one from another group, but it has been very difficult to reproduce, essentially because it's very difficult to control these oxide layers. So, I mean, I was coming a little bit from this transport community, as most of you are belonging to, where we make contact to single molecule with the STM. And at that time, I was wondering whether it was possible to combine this contact experiment with light emission. And of course, the first problem you met is as soon as you contact a molecule, then you're quenching its fluorescence. So how do you decipher that? And the idea came by the paper of Fluorescence, I think, unfortunately, it's not quoted there, where they lifted one of this very long wire in the STM junction. And that's something we try to do. I will be relatively fast with this, but just to give the flavor of it. So we work with polythiophene, another molecule we have seen before that we deposit on surface. And we were able to make them on surface and then to contact them with the tip and to lift them into the junction. And we ran a current through this molecule. And we were lucky enough that you have a part here of the molecule that is sufficiently decoupled from the electrode that it's able to emit. So this is the idea. You have a part that is in the center of your wire that will emit some light. So that worked relatively well for the thiophene, but it worked even better when we put in the middle of the wire another chromophore that is a porphyrin again. So this is the copolymer made of porphyrin and thiophene. Then you can reach this configuration where you have this molecule that is in between the two electrodes and quite well separated from the electrode by this wire. And when we did that, then this is the type of optical spectrum you obtain with a very sharp resonances, even some vibronic peak in the side. So something like a monochromatic molecular LED, so something that really emitted a given energy and still suspended, still in this contact configuration that we all want. The only problem is that those systems were extremely fragile and do not emit so much light. So this is why we went for something more robust. So these are graphene nanoribbon. You have seen them quite a lot, I think, in the literature in the last 10 years, more or less. So you can build this graphene nanoribbon in the junction, and for given widths, this behave as semiconductor which can emit light in the visible. So we just use this wire, we suspended them in the junction, and this is, actually we could see some light from those systems quite efficiently They emit it not so efficiently, but they emit quite a lot of light because they're extremely robust to high current. So we can pass high current, still have some light. And I would say if we think in terms of device, this is the closest we could go with this STM configuration. So maybe device is a little bit too much, but still we could see light nearly with our own eyes from a single ribbon. So I think it's quite relevant. Good, but this is not what I really want to speak about today. I mean, I want to go on this idea that we can use STM to make hyper-resolved fluorescence microscopy so that we can get really a type of optical microscopy with STM. So I mentioned this work from Wilson Ho, and I mean, this work or this field has known some revival in 2016 with two papers from this Chinese group, Zhen Xiaodong, that was mentioned before, and simultaneously in this Nature article from Japan. So I think they have a couple of months in between both of them. When they used here a thin salt layer to separate the molecule from the substrate. And that, I mean, was so trivial that I really wonder why nobody did it before. Actually, why we didn't do it before, but whatever. But it worked much better than with oxide because you can move your molecule more easily and it's more reproducible, as you will see. And from there on, as you can see, there has been a couple of papers in this field, and there is much more coming out. So I think it's quite booming now. Good. So just to give you some idea about what has been done in this field. So this is the first paper, so the one from the Chinese group. So they have this zinc phthalocyanine on salts on silver, so only plasmonic materials. So the salt indeed decoupled the molecule from the substrate. And what you have here is this phthalocyanine on salt. They put the tip at this location on the molecule, and this is the optical spectrum they observe. It doesn't look so impressive here, but actually it's quite nice because you have only one emission line there that corresponds to the fluorescence of the molecule. So by this way, they just run current, they see the fluorescence of the molecule with a very simple system that everybody can reproduce. That was already nice. But this is not all in this paper. Actually, the most fascinating aspect is what happens when they put a second molecule. So they just drive another molecule in contact with the first one and excite the first molecule exactly at the same location. And this is the spectrum they obtain. So now the peak that was the fluorescence of the molecule is splitted. And their interpretation is that you have a hybridization between the dipole of the two molecules. So you have a coherent coupling in between these two dipoles that gives rise to these two peaks here. So this is something quite fascinating that you can observe that directly at the level of two molecules thanks to this technique. Good. I also mentioned this group from this work from the Japanese team. So they used basically the same system. They just used two different molecules, one H2PC, one magnesium PC. Actually, one has a slightly higher gap than the other. And what they show is that by exciting one molecule, they could see the fluorescence of the neighboring one. Because you put this molecule to the excited state, and this can decay to the low molecule that acts as an acceptor. So energy transfer in between two molecules and emission. Yes?
So are these STM images?
Sorry?
Are these STM images?
Yes, so this is STM images. You can see H2PC, MGPC. And here you have a close-up view of this dimer. And they just play with the distance between the two guys and they approach them. And what they see is that, I'm not sure I can connect the two exactly now, but I think for this configuration, they excite MGPC. So they see essentially MGPC and a little bit of H2. And as soon as they put them closer, I mean, this energy transfer becomes more efficient.
How could we do STM on NaCl?
Okay, so it's not, as you can see here you have a bit of silver, and here you have 3 layers of NaCl. So it's a very thin barrier. Yeah. So it's not sufficient to prevent tunneling, if you want, but it's sufficient to decouple the molecule from the substrate. And actually, that was one of the difficulties in our field for light emission to find something that has the good balance between both. Good. So you can do an energy transfer directly at the level of 2 molecules. Okay, so this is where we stepped in. So as first, we wanted just to reproduce the results, and we were also interested, as I showed you before, by some vibration that we saw on our lifted configuration, and we thought, okay, it would be much better to have something where we can image something. Good. So what we did is we started with the zinc phthalocyanine on salt again, and we made this trimer of molecule, and we just put our tip here on the side of one of these molecules, and this is the optical spectrum we obtained. So here you have one very intense peak around 660. This is the fluorescence of the molecule, the S1 to S0 state. But when we looked here in the red side of the spectrum, we also see some tiny wiggles that look like noise. But when we improve, or when we focus on this signal, we can see that we have a lot of peaks actually with very well-defined energy and intensity. That looks like vibrations. So our first move was to try to compare this to something. And this is what you obtain that what we obtain with Raman spectroscopy, so now it's on bulk molecule, it's not something localized below our tip, but this is the Raman spectra of the molecule. So you can see that you have in this Raman spectra a lot of peaks that match very well in energy and position, and also relative intensity, the one we have in the spectrum. So what Raman spectroscopy gives you is a fingerprint of your molecule, all the vibration of your molecule and their intensity in this optical spectrum. So this is quite nice for us because in general in SEM you don't have any chemical resolution, but this is something we obtain here in our fluorescence spectrum. It's not Raman, it's still fluorescence, but we can see that we have exactly the same type of information, but directly at the level of a single or a couple of molecules. So we have a kind of chemical resolution together with STM by this approach. So that's already quite nice. What is even nicer is that with STM you're not limited to probe one position on your system. You can consider your molecule as an extended object and check different position on this object. So that's what we did. So we move our tip on 3 different locations on the left molecule that you have here. And this is the 3 optical spectrum we obtain. So if you look into detail in this vibronic feature, you can see now that there is some differences and similarities between this spectrum. So for example, you have a couple of peaks that have the same energy and also the same intensity in the 3 spectrum. And they all belong to what we call A1G mode. So this is purely symmetric mode, vibrational mode of the molecule. So nothing special there. Maybe more interesting is what happens to this B1G mode. So these are antisymmetric mode that look more or less like that. But you can see that they are quite strong in the top and bottom spectra and relatively weak in the middle one. Sorry.
Are these at low temperature?
Yes, sorry. Yeah,
So
it's all 4K.
At room temperature, they'd be washed out.
Yeah, well, at room temperature would be for us very difficult to do the experiment. But if you look in Raman spectroscopy, this is done at room temperature, for example. So it's not something we could reproduce experimentally at room temperature, but I'm not sure we would have something completely different. I mean, it would be larger, of course, but it's not like it would disappear completely. Or it should. Okay, so we have some differences for these modes. We have other type of mode that are B2G, another asymmetric mode, and then in this case they are very strong in the middle spectrum and very weak in the top and bottom. So, I mean, this is somewhat interesting. It seems that depending on the type of mode we have, we don't have the same intensity as a function of position. And already this should raise some question. I mean, I just mentioned before that the Raman spectrum or the spectrum we had is a kind of fingerprint of my molecule. Now, depending on where I'm looking at my molecule, this fingerprint is changing. So, I mean, this is something that is already not expected so much. But for that, of course, you have to be able to look within a different part of the molecule. So you can go beyond that and do some imaging now. So rather than just focusing on 3 different locations, we can acquire a spectrum for each position of the tip with respect, in this case, with a molecular dimer. And we can show how the intensity of one given mode changes as a function of position. So for this B1G mode, you can see that it's very intense following this S shape and very weak in this position there. Here, for this B2G mode, we have the opposite configuration with a kind of Z shape. And well, definitely not working as I want. And for the A1G mode, we have something more symmetric. So again, we find back this feature that depending on the mode you're looking at, the symmetry you have is different. And for a different B1G mode, we find something relatively similar. For the B2G as well. For the A1G, it remains more or less the same with some attenuation. So this is what we could say that we have here some kind of vibronic spectroscopy with obviously submolecular resolution, and this is what I've called a hyper-resolved fluorescence microscopy. Yes?
Could you remind us quickly what you do experimentally? So you put your tip at a certain position, you keep it fixed there,
Yes.
and then you scan the source drain voltage? And
No, you don't have to. No. I mean, it's like SITS, but you don't have to change the voltage. What you recall is an optical spectrum. So what I do, I put my tip somewhere, and I just collect the light over a given time, so 2 minutes, let's say.
What would happen if it would change source drain voltage? When you keep it fixed, you tip fixed, and then you put the other voltages to source drain.
What do you mean? For the light?
Tip the substrate, and you would just scan and make an IV curve.
Bias difference.
What would happen then?
Well, you would have a SITS image of your sample. I don't know what you mean you want.
If you change source drain voltage, you change energies. Huh? So the,
Yes.
electrons will come through, they have different energies. So what would happen with your spectra? When you
For the light emission, okay. Well, before doing it as a function of tip position, this is already something to do at a given position, and already the voltage dependency of this signal for a given position is not so trivial. I mean, I could discuss it. You would see different onset, different moment where you start to see some light emission. You would have a first onset when your voltage just hit the energy of this transition. So you have this indicates some kind of energy transfer mechanism. So an electron that just gives its energy to the exciton that eventually give light. And you have some other onset, for example, when you start to hit some orbitals with the voltage, then you can have some enhancement of the luminescence. But this is extremely dependent on the system you're looking at. Different molecule, different substrate, different behavior.
But when you make a spectral like this, how you choose on this?
The voltage, okay. You choose it in a way that you have a lot of light. That's the first thing, okay? And in this case, we used -2.5. So in this case, we are both resonant with the orbitals, the molecular orbitals, let's say, and also we have this energy transfer. But the mechanism is in general is something that is heavily debated. But we can come back maybe later with this. I mean, the idea here is just already to say that you have some optical resolution with this, at least to some extent. Good. So we can compare this to what Javier showed us before, the Raman. So you have here, the Raman images that he shows us, so a laser that is shined on this tip sample junction, so some kind of amplification at the junction there, and the Raman signal that is re-emitted, and then they also see this vibration, and they can also resolve them spatially. So these are the results of 2013. So you have here maps for different modes. Well, there has been now some new results actually from a group in the US, from Abkarian's group. There is also another paper from Zhen Xiaodong right now, where they start really to see for different modes very different signals. So something that I think is quite amazing. And well, I mean, here we just have another way to look at this vibration and locally, but without exciting the junction with a laser, just with electrons. Beside that, I didn't give you a final explanation for that because we just don't have it. I mean, this is still something we try to understand. What gives us exactly this contrast and how to understand it. Good. But anyway, what we have here is we have a way to combine spatial resolution and spectral resolution in an STM. So what can we do with this? And what I will show you is that we can probe different type of chemical reactions there. So starting with what I will call tautomerization reaction. I mean, I hope there is no chemist because they don't like it to be called chemical reaction. But whatever, the idea is that we can probe what happens, for example, this free-base phthalocyanine with hydrogen that move from one side to the other. And you will see that we also will understand a bit better about, a bit more about this resolution that we have here. Okay. So this is the results from the Japanese group on this same molecule. So they have seen, you have here a fluorescence spectra of this molecule. You can see that there is lots of different features here. You have here one very intense peak that is named the QX, that is a dipole that is along this two hydrogen in the center of the molecule that is oriented like that. You have a QY dipole that is perpendicular to this one that corresponds to this peak here at higher energy. And you also have the vibronic feature that we just mentioned that we won't discuss much now. So we will just concentrate on what happens here. So what we did, we tried to reproduce this data. So we have here H2PC. This is an STM image on salt again. And we first put our tip in this location, 0.1. So you have here the optical spectrum, look very similar to what we could see in the literature. But when we put our tip on the second location, here we have this spectrum that is still not too far, but if you look into detail, well, you can see that there is some kind of shift in the position of this peak. And actually, if we come in the middle of the molecule, then we see now that we have more feature. Actually, it's not a shift, it's like we have a split of the peak or a duplicated feature. So how to understand that? So what do we have as a tool to understand such feature? The first thing we can do is we can image. We can make this photon map that I showed you before. So this is a topography of the molecule. And we for each position of our tip with respect to this molecule, we just record the light emitted at this QX1 contribution, so the intensity of the light. So this is the related photon map. So this is what you obtain. You can see that you have very intense feature on this side and this side of the molecule, quite of a node here, and also some submolecular feature here. So that's it's not helping so much if we have no interpretation. So that's why we work with Thomas and Javier that just presented before. And this is now how we understand a little bit those maps. So if you want to understand the light emission in an STM junction, you have to combine two things. So light intensity is proportional both to your probability to excite the molecule at a given location, time your probability to emit. Okay, it's always the two things, the electron and the plasma that I mentioned before, as you will see. The probability to excite the molecule, you will have to believe me, follows the HOMO. So this is where your question comes into account. We are resonant with the HOMO. And what you see is that if you're getting on top of one of the lobes or in between lobes, you will have a higher probability to excite your molecule or not. Okay? on that you have to believe me. But this is the reason why we will see we have this submolecular resolution here. And for the second part, which I think is the most interesting for us, because everybody knows that STM can do submolecular resolution, is related to the plasmon-exciton coupling. So this allows me to put the molecule in the excited state, and now I have to radiate to emit a photon. And that depends on this plasmon-exciton coupling that just Javier mentioned. And just to give you a little bit another view on this system, so this is a paper. You're on this one too. Okay, so this is the view of having a gold tip and a gold film that's, well, maybe laid back to the 90s, where we believe we have some plasmon amplification that is relatively broad, relatively large, and not so strong. So we have here the field enhancement as a function of x being this position. And if you're in the center here, you have a very broad amplification of the plasmon, but you can see that it's relatively large. And so this would be like that. The plasmon would be the red stuff on top. You can excite your molecule, and you have the plasmon that couples broadly to the molecule. That would not give the result that we had. So now I come back to this paper that Javier just presented you, where he says, already in 2002, we knew that there has some subatomic scale resolution. Actually, if you read the paper in detail, what you find is this. The shifts are detected up to lateral distance of 50 angstrom from the step, which is consistent with the model calculation for the extension of the mode at the cavity. Actually, at that time, what people believe is the spatial extension of the plasmon is about 5 nanometer, not better. So the revolutionary aspect of the work of Javier later on is that to consider that if you now just add, compared to before, a small protrusion here in the cavity, is that you have a stronger amplification, just you have this pico cavity that occurs with a very strong enhancement of the field. And this is what we are looking at. So you have here these plasmons that couple with our exciton, and depending on this coupling, the probability to emit a photon will be higher or lower. Good, and if you make the theory for the molecule we just looked at, so this H2PC, this is what you obtain. You have two very intense lobes when your molecule is located there, so you have a strong coupling between the plasmon and exciton, there and there, but when you're in the middle, you have just no emission. If we now compare to our experiments, and we just now couple this probability to excite and to emit, this is what we obtain. You can see that we have something that is very close to the photon map we have in the experiment. Okay, good. So it seems that we have identified what we have in the photon map. Here is the excitation of this QX mode of the molecule. Good. So what about the second peak we have there that I've named for the moment QX2? Well, it's tilted by 90 degrees. So, well, this is one thing, but there is another peak here that I named QY2. Again, tilted by 90 degrees. And I compare with what the theoretician gave me for QY, well, it's opposite. There is even another one that we just barely see that is, again, in the opposite. So there is a mess, somehow, a lot of peaks there. And to understand what happened, what we have to do is just to consider that we don't have one molecule, but actually that we are simultaneously probing two molecules. One tautomer with the two hydrogen in that direction, and one tautomer with the hydrogen in the other direction. In this case, you have the QX and QY for both molecules that occur. That very well match the one in the theory. But that's just an hypothesis, so yeah. 2 minutes. Wow, okay. Good. So, so what we believe is that we have this configuration. The tip is on top of a part of a molecule, and we have this hydrogen that are switching in and back within the molecule very fast. So, but to prove that, we would have to resolve in time our system, which we cannot do with a CCD, with a spectrometer. So what we did is we just changed the setup slightly just to add two APDs here that are able to collect photons and to correlate them in time. And what we do is we split the signal in two here, and we had some filter here. One that we just let the blue light pass, so the one from the QX2, and the other one, the red one, so the QX1. Of course, they are not blue and red, but just to tell you that we can select for each detector the light coming from one of these contributions. If you do that, and you make now the time lapse of the signal, so what you have here is the signal on APD1, APD2, as a function of time. And each of the bars correspond to a single photon. What you can see is that there is a moment where there is a lot of light on red, and then nothing at all, but then it's intense on the blue, and so on and so forth. So when one contribution is intense, the other one is at zero, and opposite, when one is at zero, the other one is intense. And actually, this also matches what we see in the current, and that's what that shows is that the molecule is flipping from one configuration to the other, and we just see the light coming from one tautomer or from the other tautomer. So we could follow in time somehow the fluorescence and the tautomerization of this molecule. We can make some statistics out of that, so correlation and anti-correlation of the signal that just confirm the thing and gives us also time the molecules spend in a given configuration. That depends also on current. But somehow we could show that we can combine fluorescence and some time resolution. We can do much better. Some people have done much better with time resolution, but this is already something that is not too bad. Okay, so I guess I will have to skip completely the next part, which was about how can we charge a molecule and see a charged molecule. But well, quite a bit, huh? So we can do things at distance. We can discuss what Javier has told us before. Well, maybe this is one part that is interesting. This is eventually the final things, how we understand this emission process, which is that we have the tunneling junction. So as Javier said, we can excite the molecule at some distance. This is something we have reproduced. And when an electron decays, this energy is lost and can be transmitted either to the molecule that is in the cavity, so that would be an energy transfer to the exciton, or to the plasmon. And both are coupled now to each other. And finally, you see the light. And this is the origin of the Fano factor you have. You have two paths for this excitation to go, either directly to the plasmon in emission or by the exciton and the plasmon. And depending on where you are with respect to a molecule, then you would go from a dip to a peak because of this change of Fano factors. Good, but I think that was now too fast, and I will just switch directly to the conclusion. So my aim was to show you that we can make some hyper-resolved fluorescence microscopy, that the signal we have is purely optical, and I think this is really important because at first people only believe in STM that the resolution came from where we inject the electron, which in a sense would be uninteresting because this is what we are all, well, it's interesting, but it's only interesting for people doing STM. But there is some optical resolution beyond that, and this is what we are trying to look at. And I hope I could convince you that we can go below the nanometer scale with this. And of course, out of that, I ask you, what can we learn? So there is a lot of things. We can have some new things that are submolecular fluorescence microscopy. I mean, not very clear so far what it means. We can have information on charge species, so some chemical information on other chemical reactions, such as the tautomerization. People have seen energy transfer. I think this is very important. And you can even look at quantum emitters, but I won't discuss that now. And I show you we can also build some small component out of that. Okay, just a few people I would thank, especially the 3 PhD students, so Gaël, Michael, and Benjamin, who are the 3 PhD students that were directly involved in all this field, and all the results I show you, and all our collaborators, so theoreticians in Strasbourg, in San Sebastian, I don't have to present them, photophysicists in Strasbourg, and some chemists in Paris. And with this, I thank you for your attention.